specific questions yesterday at the end of the class, or when we were having the little break at the end. But they were pretty specific questions. So nobody has anything else to bring up from the other day? Okay, we can move forward then, no problem. Let me switch slide decks real quick. So today we talk about conformations. Conformations are really important for medicinal chemistry. So when we think about an enzyme, enzymes are composed of amino acids. Amino acids are mostly chiral molecules. There's one that isn't, right? Glycine is not chiral, but all the other ones are chiral. So when they form a pocket in an enzyme or a receptor, or some other biological target, maybe it's RNA or DNA that we're trying to engage, that's a chiral environment. And so that we nowadays think very much about the chirality of drugs and how drugs will fit in that chiral environment. And fluorine can perturb conformation significantly, and that's what we're going to talk about today, how fluorine can control different conformations. We'll talk about sp3, carbon-carbon bonds bearing fluorine. We'll talk about some other amides bearing fluorine at the alpha position or ortho position of an aromatic ring. We'll talk about how different functional groups engage fluorine differently and help control conformation. Amines, hydroxyl groups, other fluorine atoms. There'll be a variety of different control elements that we'll be talking about. And so again, this is just to help prepare you to think more critically about how to exploit fluorine in medicinal chemistry. So just as a reminder, and I'm going to keep hammering this, the physical organic chemistry is extremely important to understand. And by understanding the physical organic chemistry, you can apply it more intelligently in the design campaigns that you'll be working on in the future. And maybe it's your PhD work, maybe it's your postdoc work, maybe it's in 15 years in industry, or when you're mentoring students, when you're a faculty member mentoring students and you come back and start talking about conformations and how to improve the quality of interactions with between your drug and your target. So specifically today, this is the roadmap. We're going to be talking about linear and cyclic systems, and we're going to be talking quite a bit about a few different types of interactions. We will be discussing hydrogen bonding interactions, and I'll say several times in this course, inter and intramolecular hydrogen bonds are very different with fluorinated substructures. And so in this lecture today, we're going to be talking about the intramolecular hydrogen bonding interactions. We'll be talking quite a bit about dipoles. And in order to understand the dipoles, we'll talk quite a bit about magnets. And just think of like back when you were a kid and you're playing with magnets in the house, in the kitchen, the bathroom, wherever you're playing with magnets. Think about how those interacted, and we're going to come back to that analogy when we talk about different orientations there. And then we'll be talking about quite a bit about Newman projections and how fluorine can help control the different substituents around a CSP3 bond. Okay, so that's the kind of roadmap for what we'll be talking about. And we're going to start right away with that final topic that I just mentioned here, looking at CSP3 bonds. So fluorine can control conformations, and specifically, we need to draw an analogy to, first, I want to reintroduce an area that you all are likely more familiar with, and that's like if you had an oxygen there, and then we'll compare it to what happens with fluorine in the second step. Okay. So when we look at maybe a compound that has a hydroxyl group in it here, we typically rationalize the more favorable conformations through an anomeric effect. Anomeric effects would be something like a lone pair of electrons on the atom that's on the back side. Remember, this is a carbon atom on the front, and then in the back you have another carbon atom, and so that group is attached to the carbon atom in the back. And this would be a lone pair of electrons. Those lone pair of electrons donate into the sigma star orbital of the CO bond, and that's a stabilizing interaction. Okay, so it's a really basic phys-org principle. that anomeric effect encourages the molecule to exist in the conformation in which that lone pair is anti to the hydroxyl group. And for oxygen-containing compounds, you'll typically see this anomeric effect override gauche interactions. Now for fluorine, the opposite is true. Fluorine prefers to exist in a gauche conformation. So gauche meaning these are 60 degrees apart, the X and the fluorine group. And so the equilibrium here will lie in the opposite direction. That's an important conformational control element for the simple model system. We just have hydrogen, 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 hydrogen around the ring. But in other situations, you might have other carbon substituents or other things that are built around the drug or your materials, right? So the gauche effect dominates over the anomeric effect when you have fluorinated compounds. And in order to rationalize that, we use several different models, energy orbital overlap diagrams, and also this type of a visualization. So specifically, we can start with this one over here. Again, we're looking at the gauche conformation relative to the anti-conformation. The gauche conformation is predominantly stabilized by vicinal CH bonds donating into the sigma star. So this is the sigma bond. Remember, there's a big sigma star over here on the back side of that orbital, and it's a donation of the sigma CH into the sigma star of the CF. And that's a stabilizing interaction. That interaction is shown over on the other side of the slide. You have 2 electrons in that CH bond. Those are there. There are no electrons in the sigma star of the CF bond. That would be the one that would be presented right here on the back side of that would be in this space. Okay. And the donation of those electrons into the sigma star creates a hybrid molecular orbital, and 2 electrons will go down into the hybrid orbital. When we make a hybrid orbital, because of orbital conservation of orbitals, we make a bonding orbital and an anti-bonding orbital. And so we have 2 electrons that go down into the bonding orbital, and no electrons go up into the anti-bonding orbital. And as a result, we have a net stabilization of this conformation over here because of this type of an electronic configuration. Okay. So this is basic phys-org bonding theory. And that's the reason why this conformation is more stable. You have to have a CH bond presenting into the sigma star. When that CH bond presents into the sigma star, that will mean that the X group and the H, in this case for this model, are at 60 degrees relative to the fluorine atom there. Okay, so it's an important conformational control element. Now, how strong is that interaction? That's going to be important. How much of a rotational barrier is there to overcome this interaction? And that's what's shown on the bottom of the slide. That X group can be many different things. There's no shortage of things that you could imagine there. And so we're just going to scan a subset of these groups. You can see if you have a fluorine atom there, so that would be like a vicinal 1,2 difluoro-containing compound. That energy is reasonably low, half kcal to 1 kcal per mole, usually. Okay, that definitely gives a preference for one conformation relative to the other, but it's reasonably weak overall in energy. Similarly, if you just have a hydroxyl group, that's a reasonably weak interaction. As you get to acetates and the inverse ester, right? This is an ester that's also an ester, but they're connected differently. One's connected through oxygen, the other one's connected through the carbon. So those about a little over kcal, kcal and a half. And then you see this massive difference in conformational control energies when you look at neutral versus cationic species. That's a really important difference there. When you get charged amines, any charged species, you see this massive preference for the gauche interaction. Really important. We're going to look at that in more detail in 10 slides or so. It'll be a little bit further down, but we're going to come back to that. That's a really powerful control element. Okay. Amides, pyridines, you can have other things there too that help control the conformation. And these are just estimates for a model system. Any specific system where you have other groups dangling off your molecule, there might be perturbations to the overall energies there. Okay? So that's a really basic principle here. That's the first basic principle. The second one comes back to dipoles and magnetism. So this is going to be a slightly different model system. This is a model system in which we have a series of carbonyl-containing compounds and a fluorine atom at the alpha position. In this model system, we have a variety of different groups here at this position. You can see amides, esters, ketones, aldehyde. This type of a system prefers an orientation in which the fluorine atom is actually aligned anti to the carbonyl oxygen. And this is the situation that I had mentioned before where we're going to think about magnets. And if you are a kid and you're playing with magnets, you've done this before. Okay, you have your magnets. They have a positive and a negative side. We know about what sides engage each other and which sides repulse each other. You ever try to hold them together, fully aligned? They don't like that. You ever try to hold the bottoms together and see what happens with the tops? The tops push away. And they'll push away as much as possible. And that's the same effect that you're seeing here. You have the carbon-fluorine bond as a dipole. You have the carbon-oxygen bond as a dipole. Carbon-oxygen double bond, right, and has a dipole. The dipoles they're cationic on the carbon. They're anionic over on the fluorine or the oxygen. And so when we look at this model, we can see that you can't change the distance between the positive side. Regardless of what conformation, those are held at a fixed difference. But the anionic portions, the anionic repulsion, can push the oxygen far away from the fluorine as much as possible, and that's what we're seeing here. Okay. So it's an electrostatic repulsion effect that gives you these energies. Those energies inversely correlate with the electron density on the oxygen. We learned this when we think about early organic chemistry and electronic structure, is you have a carbonyl and you have substituents with lone pair of electrons that can donate into the carbonyl. That increases the anionic character at oxygen. And so that increases the strength of the dipole. When you increase the strength of the dipole, you're going to have greater electrostatic repulsion here. And as you go through the series, oxygen can still donate in, not as well as nitrogen, but you see a little less electron density on oxygen, a little lower repulsion energy there, conformational control energy. Ketones, no lone pair of electrons. They cannot donate in through some type of a hyperconjugation of lone pair of electrons. Nonetheless, the carbon is still somewhat donating into the system through a sigma effect, and that's what you see here, and the aldehydes are way over there. Okay. So that's one important effect, this electrostatic repulsion really pushing the electronegative atoms away from each other. Now, in another model system, we can also see that hydrogen bonding, intramolecular hydrogen bonding, can further reinforce conformations. So in addition to the dipole repulsion, this model system that we're looking at here, that has an amide, alpha carbon with a fluorine atom, and then some other group attached, this model system can have several conformations. The most stable conformation is the one in which the dipoles of the CO and the CF bonds have, again, rotated away from each other. But this system also benefits from an intramolecular hydrogen bond. The intramolecular hydrogen bonding does happen, it is real, it is a real effect in fluorine chemistry. It's not particularly controversial. Now, as we rotate around the CC bond here, you can rotate it such that we lose the intramolecular hydrogen bond, and those dipoles between the CF bond and the CO bond come closer together, 6 kcal per mole. That's a lot. And here's another example where we further rotate the molecule. So this is from here to there, that's 180 degrees. And again, those dipoles start to align. And that's disfavored, 8 kcal per mole. That is very, very, very unhappy. Okay, if you want to do a quick calculation in your free time, you can take 8 kcal per mole. RTLNK, what's the equilibrium? What's the ratio for 8 kcal per mole? This thing does not exist. Okay, go do that math at some point. 8 kcal per mole, what's the equilibrium distribution of those species? And rationalize to yourself how powerful of an effect that is. Okay. So in this case, we have 2 things reinforcing. Now think of how you might exploit this in a drug discovery campaign. This model system has methyl and methyl. Methyl on the amide, methyl alpha to the amide. If you have bigger substituents built onto that engage your biological target, heterocycles, arrow rings, other pharmacophores you might have, you can really encourage a conformation in which we have control of the stereocenter, which might benefit engagement with any particular target. Okay? So we saw yesterday in the synthetic lecture some of those alpha fluoroaldehydes and other carbonyl-containing compounds, and you can really build around them very well when you can make them enantio selectively, and that can be a really powerful conformational control element if you use it. Okay? So I'll pause. We went through a couple of effects. We went through the gauche interactions. We went through these that are an electrostatic repulsion and then combined it with an intramolecular hydrogen bonding interaction. I'm going to pause and see if there's any questions or.
In the first case, even there is in the case of OH, okay, so there also there is a dipole because CO. So why that doesn't predominate?
Sorry, in this one here.
Yeah, like for example, if you take these 2 Gauss effects predominate those pictures, so because that OH dipole and our CF dipole. So
Yeah, so
anti-form also.
Maybe one thing when we talk about a lot of these oxygen-containing compounds, when we're thinking about what is the X group, most commonly it's lone pair of electrons that we're talking about, like sugar, saccharide chemistry, and things. So the nature of the X group in these cases is usually lone pair of electrons is great at hyperconjugating into the sigma star. Yeah, it's a key difference here. In contrast, if you have fluorine and you have lone pair of electrons that are nucleophilic, what happens, say we have some type of a functional group that allows us to make a full-blown anion. These are not particularly stable. If you have lone pair of electrons alpha, they'll typically push off your fluorine. And then you get to some type of alkene type species. If it's instead like a nitrogen without a proper protecting group, same thing, lone pair of electrons will give you an imine. If you have a hydroxyl group, if it's OH, lone pair of electrons will push off your fluoride and make an aldehyde or ketone depending on what else is attached. Similarly, if you have like OMe or something like that, less of an effect. So there are lots of nuances as you continue to build and build and build on it. Yep.
So I didn't quite understand that the middle panel. So the sigma CH bond, the sigma electrons can actually participate in the gauche form. Yeah, this one. Yeah, this one. So you can actually have that little stabilization which is coming up. But then this one, the bottom one, when you have this anomeric form, so why that CX cannot really donate into that because it's a mismatch in the energy of the orbital, or how is it? Why is this?
Yeah, I think it's an orbital mismatch, and so when you have the CX, it's like an oxygen or fluorine or something, that bond gets stabilized quite a bit more.
Okay. And anyway, the
and so it doesn't.
That one is very high,
and that would be
this one's down. So is it this? Because of the orbital mismatch, it doesn't happen. That is disfavored.
Right. Okay. You want to be thinking about orbital mismatches for sure. Yep. And these are all, you can use quantum mechanic, Gaussian, and things like that to estimate specific examples too. And you can see these types of interactions when you do a Gaussian calculation and you look at the different orbital energies. You can see these interactions pretty clearly.
But then, so this you are deconvoluting this effect completely with the electrostatic repulsion effect. But in a way, this combines with that to give that, right?
Yeah, depending on what type of a model system you have versus your real system, you can have several effects reinforcing each other, or they can be working against each other. You can also design systems that work against each other, and then you kind of get like no effect, right? Or minimize each other, right? So I think any of these effects, you want to be really critical at how you think about use them think critically when you're trying to use them in your molecules, right? Because they can be working against each other or they can reinforce each other. Yep. Okay. So this is maybe the first example, and this is going to be an initial example that we're going to cover briefly, but the tutorial today is there's a lot of stuff in there. We're going to come back to this exact molecule in the tutorial. So my discussion right now is going to be maybe a little bit more brief than it should get, but it's because we're going to come back to it. So this is an approved therapeutic, not used very much anymore. It's an older therapeutic. I think it was approved in the early 90s, indinavir. It's an HIV protease inhibitor. You can recognize a lot of these HIV protease inhibitors by the secondary alcohol right in the middle of the molecule. And as a protease inhibitor, the role of a protease is to cut up peptides, right? And so those peptides have a bunch of amino acids. And the proteases recognize very specific amino acid sequences. So they have certain pockets. We call them S1, S2, S3 pocket. If you go one way, S1 prime, 2 prime, 3 prime, and those are pockets in the enzyme that fit very specific amino acid sequences. And when these HIV drugs, when you look at them, you see that secondary alcohol, but you also see certain moieties that fit into the pockets that a peptide side chain would normally fit into. So these are either peptide-based or peptidomimetic drugs, typically, for these HIV protease inhibitors. And this is one of the first generation ones. This thing gets metabolized so quickly. Patients have to take 4 rounds of drug a day for like every day of their life with these older generation agents. And the newer agents have solved a lot of the PK problems. Anyway, this story is really going to be about conformational control over a linear system. You don't see as many drugs that have these really long linear systems because they're typically so flexible, they're very wobbly. And in this case, in these HIV protease inhibitors, many of them do have extended aliphatic chains. So this drug itself has a Ki value of 1.9 nanomolar, so pretty potent of a compound there. Interestingly, when you switch the alcohol, you change the conformation. And when you do that, look at the inhibitory potency there. Pretty drastic change, right? 80-fold change just by one stereo center. So what difference does a stereo center make? It can be pretty powerful when you get it right. In this example, this is an older example from '86, the introduction of a fluorine atom alpha to that alcohol in this species here, the active drug, gives you no benefit, 2 nanomolar still. And within the errors of the measurement, that's probably the exact same number statistically. So no benefit. Why? I'm going to talk about that in just a second. Let's look at the other one. In contrast, when you have the secondary alcohol over here, you can put a fluorine atom with appropriate stereochemistry and rescue quite a bit of the activity. 8-fold improvement by a fluorine atom. So what's going on in the system? Let's think about what section we're on. We're talking about conformation control and fluorine. I've introduced this gauche interaction. What's going on in this system, the molecule needs a certain conformation to fit in the protease pocket. When we introduce a fluorine atom here, we get no gain in potency, and that's because the introduction of the fluorine atom will favor a gauche interaction. But if that's already the natural conformation of this drug, if it already sits in that same conformation, you really don't get much benefit. It had the right conformation before, it still has the right conformation, everything's good. In contrast, when we go to this derivative over here, you have the wrong conformation. That alcohol's in the wrong position, wrong stereochemistry there. And so in order to get this type of potency, it's even got to like rotate around unnatural poses to engage in the target. But we can encourage this molecule with the wrong stereochemistry to exist in the right conformation as much as possible using a fluorine atom. So we can just force that to go back to its normal conformation. Now that's vague. It's a little bit nebulous right now. Who knows Newman projections, right? Everybody knows Newman projection? Please, everybody, right? Even our master's students are early in their course, you know your Newmans, right? Okay, good. And we're going to do that in a complex setting in the tutorial. So you're going to explain this in more detail in a little bit, so get ready for that. Okay, so are we good with this more complex example for a bit? We'll come back to it. Any questions you want to address now? Okay, let's keep going. So conformation can also control ring systems. So this is a ring system, a pyrrolidine ring system. In this model system, you have a carbonyl at one position, you have an amide over here. We have 6-membered rings. We're talking about bow conformations and chair conformations and chair flips, and 5-membered rings are typically a little bit more simple. You really have 2 puck rings. You have one puck ring in which the 5-membered ring, so if these 3 are kind of close to coplanar, then you can pucker the ring one way, or that carbon can flip the other way, and that's what you see here. So you have 2 different envelope conformations there. And they can interconvert, and fluorine can control which one of those predominates. Now, when these, so the naming that I'm going to use, the exo and the endo, the exo really refers to the pucker being away from the carbonyl, and in this case, the pucker is close to the carbonyl there. So it's the endo-exo there. Fluorine can control the energy levels of these 2 conformations. So if you need, for example, a conformation that's exo, we can decorate this ring of fluorine and encourage that conformation, and we can do the same to promote the endo conformation also. Okay, so how are we going to do that, and why does it work? So here's that model system, and we can fluorinate the C4 position here. So I'm going to start here, 1, 2, 3, 4. This is the C4 position. In this case, we're going to look at compounds having either a hydrogen, a fluorine at these 2 positions. So if you have the non-fluorinated species, you have a 1 kcal per mole preference for the endo conformation, and that's this one over here. There's a slight preference for that to exist endo. When you introduce a fluorine atom here at the X group, and I've drawn it in there for you, you can invert the selectivity. You can prefer the exo conformation. That's a 2 kcal per mole change, right? It's about 1, and it goes to -1. 2 kcal per mole change. Okay, it's a useful effect to control the conformation. If we want to reinforce the other conformation, we want to reinforce the endo conformation, we can introduce the fluorine atom with the opposite stereochemistry. And that's going to encourage that to exist in the endo. Finally, if we put 2 fluorine atoms in there, they work against each other. Neither one of them wins out. You go back to 1 kcal per mole, which is equi-energetic basically for all practical purposes with where we were to start. Now, you might want to have 2 fluorine atoms for a different reason. There are many reasons you can use fluorine. We'll talk about more reasons in future slide decks. But you get no benefit for conformational control with the CF2 because they're working against each other. Now, I think it would be a great exercise. We're not going to do this here now. We're going to look at some other systems in the tutorial. But I think it would be great for you on your own time to come back and look at these systems and think about the Newman projection there and make sure you can see in your mind the anti-alignment between the CF and the CN bonds there. Make sure you can see how that maps on to that first slide we talked about. And same thing over here, it's a little bit trickier. So that was kind of, you can see that one, I think, a little bit more easily the way I've drawn it. This one's a little bit tougher to see, that there's a gauche interaction there. Okay, so that the CN is kind of down and to the right, the CF is kind of up to the right. If you build a 3D model of that, or some people in their head are just really good at seeing these things in 3D and thinking about, if I put myself, over here where this oxygen is, if I look that way, mentally, I can see what's around, and they're gauche. So I think it'd be a great exercise, ball and stick, back in your offices, in your labs. But we're going to, again, look at other model systems of this type of effect during the tutorial later, too. Okay? Questions? Comments? We doing good? Okay. So, we already covered, yep.
In ground star, in the third case, why the N2 is fluorine? Don't you think that the fluorine electrons and oxygen electrons of carbonyl will get repulsed to each other?
Yeah, I mean, that's reasonable to say the way it's drawn here, but you also have free rotation around this carbon-carbon bond, so the carbonyl can rotate and adopt a conformation which the carbonyl oxygen is not towards the fluorine. So that can happen. And I can't really draw all the different possibilities quite as well. So, okay. So you have counteracting effects there in this last one. And I want to step forward into this example. I've already introduced this gauche effect and said it's a weak effect when you have fluorine-fluorine, but it's there, it's present, it can be useful. There's another effect when you effectively use fluorine patterning, and that's this 1,3 effect. The 1,3 effect is actually pretty powerful, 3 kcal per mole in energy. You can see the representative model system we're looking at here in this 1,3 system. It can exist in a conformation in which those dipoles are aligned. That's bad, that's terrible, right? But if you rotate around one of the CC bonds, it can reorganize such that the 2 CF bonds are presented away from each other. And in that case, that's a 3 kcal per mole energy difference, and this conformation is favored. And that can be exploited intelligently, and there's some really cool model systems that I've seen out there. We'll look at a couple like super nerdy cool ones. So this is one in which we use fluorine patterning to mimic control of a ring, but we're going to remove the ring. This is really cool, okay? So in this model system, we have a dihydrobenzofuran, a methylene, and then some other moiety over here, an arrow ring in this case. The NMR structure and computational structure gives you something that looks like this. In this case, with fluorine patterning, we can recapitulate the solution structure of the molecule on the top using fluorine. So this molecule on top is pretty rigid, right? You cannot do much rotation around the bonds over here. They're pretty much locked. You get a little bit of flexibility in the ring because it's partially aliphatic. But remember, this is sp2, so you don't get as much flexibility in this molecule as you would with like a fully aliphatic system. Okay. So you don't get too much flexibility in the system. In this case, you might envision rotating around all the carbon-carbon bonds here. You have several CSP3 bonds there in a row. Nonetheless, using fluorine patterning, we can create a molecule such that the aromatic rings reside in the same chemical space. The aromatic ring over here and here reside in the same chemical space. And these are, NMR structures and computational structures that both reinforce. You have computational estimates and real data. And again, the nature of those reactions is this 1,3 dipole, and you can see that here. And this is the computational structure here. The 1 fluorine atom there, the 2, the 3 is over here, and they're rotated such that they're presenting away from each other. So pretty cool system over like that.
So in this case, the dipole, if you have 1,3 interactions, the dipole orients in such a way that the dipolar reinforcement does not happen. It actually kind of cancels it out, because otherwise there will be a strong electrostatic repulsion as well, right?
Yeah, so the electrostatic repulsion is what we're trying to avoid.
Yeah.
Yep.
So dipole of the molecule goes down, overall dipole, resultant dipole.
Yeah, so you would have a stronger dipole if they were aligned.
Exactly.
And that gives you a less of a dipole You do still have a dipole because the dipole will be the sum of the two dipoles.
Right.
Another heteroatoms and anything else,
And
but
not that in
yeah, they won't be fully additive. Yep, right. We'll talk about dipoles a bit more when we get into the lipophilicity lecture. We'll have a series of molecules that I think might interest you to think about. Okay. So that's a really cool system. Conformational control with fluorine, 1,2 and 1,3 has been used in several other settings. Here's just a couple of nice papers that one could look at that look at some simple systems. I'm going to look at this crazy looking system right there next. Just going to give you a second to look at that molecule. Right, we have a 1,2, a 1,2, right? Because fluorine 1,2, that's real with an oxygen-based group. We have a 1,3 there. We have a 1,3 there. Like there's a lot of stuff going on. And think about the synthesis of that thing. How are you going to prepare that with all the stereo control? So if you want a hint on how to do that, Eric Carrera, this paper right here teaches you how to do it. It's really cool. Something else really cool about it, and I'll come back to that in a minute. So this molecule has a very distinct conformational preference, and it can be worked out with exhaustive NMR, really thoughtful NMR. It's well laid out in the supporting information of this manuscript. I'm not sure if it'll be covered later in the NMR lecture or not. And so let's look at what's going on in the structure when they do these NMR studies and look at the coupling constants that tell you roughly the geometry, the relationship of the fluorine atoms and the other heteroatoms. So we're going to start here. This fluorine atom needs to be gauche with this one, and they are. See that? That's gauche there? Okay. Now we have 1,3 interactions. If we go from here, 2, 3, that's a 1,3 interaction. And they don't want to align both parallel. They're going to rotate so that they're, again, presented away from each other. So that's a really cool 1,3 interaction here. We're also going to have a 1,3 interaction here between this fluorine atom and this one over there. So we're going to have a pretty rigid control element all the way over here, right? And that's looking over here in the molecule. Now there's a C7. We're not worried about what's going on way over on the far side, right? We're just worried about this section over here. You have gauche interactions here between the fluorine and the sulfate there. Okay, so it's a really cool, really rigid system in which they've used fluorine strategically just to pattern this entire thing. And this is a natural product derivative, and maybe it can be useful for drug discovery, but this is like the extent of, just a really cool system, I think. Okay. I drew up a couple of other bad ones in your slides of like things that wouldn't be good. Okay, so you can think of all these other isomers and draw up crazy ones, and so in this case, if we had the wrong stereochemistry on one of these, we'd have like a poor 1,3 dipole there, because that sulfate is anionic too. So it's going to want to push away from the fluorine atom. Again, we're staying away from systems in which we have the syn alignment of the two dipoles, another one over here. So I just drew all these other things that wouldn't be good if they form, just so you can think about it. Okay? So I'm going to pause again, see how things are going. I think in your slides I gave you all these. I just didn't color code them, right? So that's for you guys. I deliberately do that for you guys to be taking notes and drawing things and being active with your slides. Okay, your notes are just kind of black and white there. Okay. Good? Okay. So let's think about what else is going on in these systems. I mentioned that there's intramolecular hydrogen bonding, and it's real. Now I want to show a couple of situations that further reinforce this concept of intramolecular hydrogen bonding and show that it's different than the dipoles, but they can reinforce each other. So that's the goal here. This is a piperidine example, a classic example again, that has a nitrogen and a fluorine atom at vicinal positions. We have the gauche relationship here when the fluorine is in the axial position. And when you do the ring flip and put that in the equatorial position, you get a lower energy conformation. That ring flip is not favorable. And usually when we think about these ring flips, we say most elements, most substituents want to be in the equatorial conformation and not the axial conformation. Fluorine's the exact opposite when it's here next to a cationic amine. So it's an important, powerful conformational controlling element when you get to the 5 kcal per mole, 5.5 kcal per mole energy there. Very useful. Now think about if you had a 5 kcal per mole preference for one conformer, you perhaps could force other substituents into axial positions that might not otherwise want to exist in axial conformation. So say we had, for example, a methyl group axial at this position. Has a pretty low A value. The fluorine would dominate in the system. So you could present things at vectors that might be difficult to do otherwise due to your classical A values. Okay? So you can use that strategically at your choosing. So this is a nice paper that establishes a difference between intramolecular hydrogen bonding interactions and the dipole, the gauche effect. Okay, so we're going to look at a series of examples here on this slide in which computationally we're looking at a gauche versus anti-conformation if we stop intramolecular hydrogen bonding. So we're not going to allow intramolecular hydrogen bonding in this interaction. This anti-conformation seems to take preference. That might be a dipole minimization type argument. In contrast, when we force a hydrogen bonding interaction, the gauche conformation, we get about 2 kcal per mole energy there. So we estimate the intramolecular hydrogen bonding to be about 2 kcal per mole, and same thing on the next one. So in this case, we have an oxygen-containing group, nearly equi-energetic, and for computational purposes, 0.3 kcal per mole is like within the error from any computations. And so we'll say these are equi-energetic. When we disallow intramolecular hydrogen bonding, we'll get a 2 kcal per mole preference for the gauche interaction when we also have the intramolecular hydrogen bonding occurring also. Okay, so we can control conformation. Again, in this model system, you only have HHHH, but in a drug, or medicinal agent, or biological probe, you can have other things dangling off the molecule and making interactions with your target. Okay, so the energy estimates for those, I mentioned before, 1.7, 1.9, that range of 1.5 to 2 kcal per mole is what you want to be thinking about when you're thinking about intramolecular hydrogen bonding interactions with a fluorine atom and an acidic hydroxyl or amine. Now, you get stronger interactions when you have cationic amines. And these become even more powerful. You can see the energies associated with these species. Again, this is a model system in which you have a cationic oxygen atom with a more acidic proton making intramolecular hydrogen bond there. You can see the energy difference is closer to 3 kcal per mole when we look at these two structures. These two calculations, one that allows intramolecular hydrogen bonding, the other one that does not intramolecular hydrogen bond. So that's one estimate. Here's another couple of estimates here. When you have cationic amines, again, really powerful conformational control here, and the gauche is always, always, always preferred. Okay? So I'm going to pause again, see if there's any questions on this series here, yeah, or the previous one, but yeah.
No, not this one only. Like in my last talk, like I was showing some data regarding hydrogen bonds involving fluorine, and it was quite interesting that CHF hydrogen bonds predominate like more. So in this particular case, the first row, so those two like methyl hydrogens, like which is alpha to nitrogen, if one of the hydrogen is replaced to methyl CH3, will it predominate in the conformational change so that it will become a CH?
Yeah. I don't think it would. Like, I think if you replace one of these methyl groups, if you replace one of these hydrogens with a methyl group, would you have a CH bond here with the CF? I don't think so. And inter versus intramolecular hydrogen bonds are very different. And so, so I think the data you were talking about was intermolecular, right? And so yep. And so the intramolecular, we see lots of examples in the literature and crystallographic database, and it's usually acidic NH-OH that engage in these intramolecular hydrogen bonds. That's pretty well established, and it's been studied computationally and solution structures, and this is well documented. But in the intermolecular hydrogen bonds, number one, I think it's actually a different effect. It's a dipole effect more than a hydrogen bonding effect, which is much weaker. And we'll cover it on Thursday, Friday. I think Friday, that'll be a subset. Okay, we will definitely go into detail on that. Okay, intramolecular hydrogen bonds are totally different. And again, I don't think there's a lot of argument in literature about intermolecular hydrogen bonds, even recently. And some people say just don't even think about it as a hydrogen bond, just think about it as positive, like a dipole-dipole interaction that's favorable. Oops.
Excuse me, sir. In one of the last examples, is there a possibility of interactions with the pi surface of the pi electron cloud? So that is where the structure is stabilized.
Yeah, so the pi interaction, yes, I think there's an interaction there. Let me point out one thing, though. In this paper, they also do a calculation, and it's a really weird calculation, because when you look at the electronic structure of that, you can see why it's cationic, right? Nitrogen with 4 bonds. They actually do a calculation where they throw an electron into it so that it's a neutral pyridine. Weird to think about what the structure of that thing is. And you lose a lot of the affinity. So in this one, the charge is really important for the alignment there. And I think you do have a pseudo cationic pyridinium in the pi system that does want more electrons, and the fluorine does have more electrons around it. And so there's an electrostatic effect there. The electrostatic effect is real.
Otherwise, there will be electrostatic repulsions between the pi electron cloud and the
Yeah. So if you had a ring here that was instead of a nitrogen, it was like a paramethoxyphenyl or a paradimethylaminophenyl, you probably see that rotate away and hate being in that environment. Yep.
So the pi electron surface should be reduced in electron density. Then only it will have an
Yeah. Yeah. And in some cases with really electron deficient heterocycles, you could invert the quadrupole, right, and get to those like a pi acid instead of a pi base. Okay. So here's the summary. Intramolecular hydrogen bonding, good. 2 kcal per mole, and a half, maybe up to 2.5 in some cases. I think we just had this discussion about intermolecular hydrogen bonding, not always great, but we talk about this in depth. So you have this slide, it's there, but I'm not going to talk much here because we're going to talk about it later. But I've mentioned this several times, there's a difference between the inter and intramolecular engagements there. Okay, so let's look at a couple more examples. Here, I do want to spend a little bit of time on this one. So this is an example in which fluorine was used to control the conformation. And in this system, there was a lead molecule that had this imide structure to it. You can see the efficacy in a cellular assay, and then the inhibitory potency in an enzymatic assay. Okay, STING immunomodulators. This is a hot area, hot target here, the STING pathway. But that's the parent structure here. Now, if you remove that carbonyl right there and go to an amide, we lose a ring system that's really holding this substituent, kind of encouraging it to present in one direction. So when we break this ring system here, now we have conformational rotation, we have flexibility around this ring system, and that thing can be it's a bit more wobbly. And you lose cellular efficacy and inhibitory potency. Okay, you lose both of those. The NMR chemical shift, this will be important just a little bit. You can see that NH bond is there in DMSO, and that's this NH right there. You can regain potency by introducing an orthofluorine atom. And you can see the position here. We make a nice little ring system. Intramolecular hydrogen bond is worth a couple of kcal per mole. And we regain a substantial amount of potency, not the entire amount, but it's still pretty good for an acyclic system that's supposed to be mimicking a cyclic system. So that's kind of cool. And you can do that the same thing with a chlorine atom there. Yeah, we can talk about that in a minute. I do want to point out, I'm going to mention this twice in the series of lectures, how do you measure an intramolecular hydrogen bond and establish that it's really there? We can speculate about them. There's a really easy NMR experiment to do. It's called ANMR. You measure the NMR in two different solvents. You measure the NMR in chloroform and DMSO. Chloroform does not engage in hydrogen bonds. DMSO, it's a base. So in chloroform, you would expect this intramolecular hydrogen bond to be really tight. In DMSO, where DMSO, that oxygen, anionic oxygen, is competing for hydrogen bonding with that hydrogen, you should see a shift. And then you can look at there's a mathematical function that compares the chemical shift in DMSO versus the chloroform, and you can establish quantitatively that there is a good strong intramolecular hydrogen bond or not. Okay, so that's this Abraham paper, ANMR. If you ever want to look that up, it's in your slide deck there. And we do come back to it, and I do actually have the equation thrown on a subsequent slide in a later slide deck, so I'll mention that a second time. But it's a really nice way to experimentally establish that you have a real interaction there. It's not dependent on fluorine. Like this ANMR does not require you to have a fluorine atom. It can be other intramolecular hydrogen bond type situations too. So it's a nice assay that can be run pretty quickly. 2 NMRs. Okay.
So I'm quite surprised to see that fluorine is doing better job than fluorine here, because I would expect that fluorine would actually have strong intramolecular hydrogen bonding, which
Sure.
in the case is bringing down to 30.3. But in the other case, the fluorine is doing better than fluorine. I mean, that's something surprising.
Yeah. So.
I expect that.
And I agree, but there's something else going on too. So when you just look at the size of chlorine and the electronic cloud around chlorine, it's bigger and bigger and bigger. And I think you're going to have repulsion between the oxygen if it tries to rotate towards the chlorine. So if you think about rotating around this CC bond here such that the oxygen would present over here, now it's going to be closer to that chlorine atom that's huge. This is all rationalization in my mind, not necessarily there's experimental data for it or computational. I mean, you could probably do a quick computational scan of the energies and see if it's a steric effect, basically, or electronic repulsion between chlorine's still delta negative, and the oxygen has a lot of delta minus charge too.
I think it makes sense because it is still providing the conformational rigidity required, because overall in 52, that is LSA 52, it needed a rigidity, and chlorine being bigger size, it is avoiding the conformational switch that carbonyl goes up, and maybe that is the reason.
Yeah, I do not remember off the top of my head, and we should probably go back in like the tea break and do a quick search, pull this paper up. I don't have my Purdue credentials. We can maybe somebody else can do this, like at the tea break. Check that Zhao, JMed Chem, who's going to be our motivated student. Do they do ANMR for compound C? Because that might establish if there's a real hydrogen bond or not for the chloride. And again, I don't remember off the top of my head, but maybe that would start to get to it. Okay, here's another example too. So the tutorial is going to take, it's going to be a long tutorial. Okay, so I'm going to skim through this slide reasonably quickly. This is the last example, and then we'll break, but the tutorial is going to be a good one. Okay, so let's quickly look at this one. This is another example for which you can see the biological probe here. We're looking at another acyl pyrrolidine system here. We're looking at the 4 position of that pyrrolidine and thinking about fluorination of that position. In this case, there's a series of compounds here. The parent compound inhibits thrombin. These other targets here are other enzymes with similar activity they're trying to avoid. So those are anti-targets where we're trying to avoid those interactions. In this case, you can put a fluorine atom here, the X position. That improves potency a little bit. Actually, you get an improvement in selectivity. And for many times in drug discovery, disfavoring an anti-target can be as powerful or sometimes more important than improving activity at your real target. You can avoid tox, you can avoid other types of things going on in cells by avoiding anti-targets. And I think that's something to think about when you look at this series of data. Many of us would look at 0.6 versus 0.4 and say, that's not that big of a change. Okay, but if we can improve potency maybe a little bit, but also decrease potency against an anti-target, that there's value there. Okay, so if you put the fluorine in there with the wrong stereochemistry, you ablate activity. So if you're ever trying this for real, maybe a lesson is, you might need to try both of them. You might not need to try only one, and if it goes terrible and everything's god-awful, maybe you just need to make the other one also and try it at the same time. And you can put them both in, and you lose activity in both those cases, okay? So there, in some cases, might be a little bit more to talk about some of these other interactions here. It'll make more sense when we cover 5, like lecture 5. But if you have lone pair of electrons from fluorine presented towards a pi-rich system, that's disfavored. Right? A pi-rich system has a lot of electron density in it. And if you put that fluorine as the dipole, the anionic side of that dipole is presented towards an electron-rich aromatic ring, you get electronic repulsion, and that's bad. So that's another reason why this is actually a bad compound, is when you put the fluorine in that position, you lose potency that way, okay? So in this case, I'm going to end here with this example. We can take our break. When we come back, you all are going to be using your pens, your papers, your iPads, your styluses, and we'll do some problem solving, okay? See some cool examples, all right? So how long should our break be? It's 11:03 now. 11:15. Okay. So we'll pause now. You all can breathe. We'll come back in a bit.